Steve, all right. So Steve's going to present a talk now on reducing uncertainty in Tephra correlations through improved geochemical characterization and better reporting practices.
All right. I think I'll just make my beginning comments over here. So, we do a lot of probe work, don't we, for Tephra chronology? I mean, that's been the go-to tool for a long time, and thankfully we don't have 87 different kinds of instruments. It's more like closer to about 4 or 5, I guess, for the probe. Although if you throw in SEM EDS data, which we have a little bit of that maybe adds a little bit more variability, but we're using this geochemistry, hopefully in conjunction with a bunch of other things, to try to fingerprint glass compositions, sometimes mineral compositions, and figure out, what tephra is it? What volcano did it come from? And so on. And so, how sure are we about this whole business? How can we tell, that the tephra from Crater Lake or Mount Mazama, if you like, from Oregon, not too far from here, is in all these places. This big, huge, visible extend stuff on the East Coast, stuff in Greenland, and stuff in marine cores and all these different places. How do we really know for sure that it's all the same? Yeah, we have some age control sometimes, but yeah, usually it comes back to that geochemical fingerprint. Major elements, minor elements, sometimes will have trace elements. Okay. So ultimately, we need to be comparing one sample to another or to a collection of samples. And so, we have this problem where sometimes those differences between things are really subtle. There are quite a few examples of this. Mount St. Helens, Glacier Peak in Washington State. There are things in Alaska and many other places where you get these very subtle differences, maybe sometimes almost nothing different at all with major elements. And so, and then maybe we're doing these analyses in 6 different labs, and and the 20-year-old procedure and today's procedure in the same lab, and all of there's some variables in there. And so we have all of this accumulated data. It wasn't all done the same way. And can we really compare these things successfully? Especially when, sometimes the differences aren't very big. Well, ultimately, precision can be important. We sort of have this slide here. This is pretty easily attainable precision, I think, to separate. 1.2 versus 1.4 on calcium is not too hard, is it? I hope. But we need enough precision to be able to separate these things. And I said, I have another example of this. And then the accuracy. If everybody is coming up with the same values on the same samples, the same accuracy, then hey, great, everything works beautifully. But we know not every lab gives the same numbers on all of these samples. So we're not necessarily consistent between laboratories. We're not necessarily entirely consistent over time within a laboratory, and that can be a little bit of a problem. Well, in order to be able to get good probe data, we have a few things we have to deal with. One, reference materials are really critical. I mean, for any kind of analytical technique, really. It doesn't matter if it's ICP-MS or microprobe or XRF or what. Reference materials are important. Even if you're doing argon dating, there need to be standards for that. And so, and in probe work, there are usually a couple of different kinds of standards. Usually there's the standards that you run when you're setting up the instrument and kind of setting essentially mapping in X-ray intensity to concentration, that sort of thing. Those are the primary standards. And then a lot of times we'll run some other standards as quality control. So maybe you'll have some minerals and glasses and synthetic oxides or various things to calibrate on different elements, and then maybe put in, an actual rhyolite tephra or an actual rhyolite glass as a secondary standard, to make sure everything really worked the way it's supposed to and you're actually getting good numbers. So those are our secondary standards. Sometimes there can be a little overlap between these things. So you maybe a glass might be a calibration standard for some elements and a secondary standard for others. That's not so important. All right. So big analytical issues, alkali element migration. This has been known for decades that if you put an electron beam on a silicate glass with a bunch of sodium in it, and the sodium counts tend to go away, down, and if it happens enough, the silicon and aluminum tends to go up. And in some glasses, potassium tends to run away pretty badly also, some glasses not so much. It's really sensitive to composition of the material, how much sodium is in there, how hydrated it is, various things like that. The analytical conditions play a really big role. And so in order to try to address this, major approaches are defocus the beam, essentially lower electron density going into the sample. Reduces the effect. So we can widen the beam to get that. We can reduce the current to do that. But wait, I have those little tiny cryptotephra shards. Nothing bigger than a 5 micron beam will fit. Okay, well, defocusing the beam to 50 doesn't help. Okay, we can't do that. Maybe so. Okay. Low current. Well, that's going to turn out to cost us later, potentially in precision, which is the very next little section down here. Other things, analyze those sensitive elements right at the very beginning. And so, don't do, have silicon as element number 6 on a given spectrometer after 4 minutes of exposure time to the beam or something like that. That's just going to really mess things up. So we have to be really careful about how the whole analytical procedure is designed. Okay. We do want precision. And again, for microprobe analyses, it pretty much comes down to X-ray counting statistics. And unfortunately, it follows a square law. So if you want half the standard deviation, you need it turns out factor of 2 lower standard deviation, you need 2 squared, or a factor of 4 more counts. Okay, if you want a quarter of the standard deviation, oh no, now we need 16 times the count. So you either need to have 16 times more beam current or 16 times longer analysis time. And if you try doing this with analysis time, your analysis times can balloon very quickly to nobody wants to do 20-minute single probe spots. It's just it's not going to work out real well. Get very little data. So maybe more beam current, again, well, but that causes more problems with the sodium thing. Well, maybe I can't do that. Well, another way around this is some instruments have larger detectors on them, larger analyzing crystals, and you can get more X-rays collected that way. And optimizing the procedure as much as possible. All right, so we're fighting our small grain problem. Sometimes you just can't get big spots on things. Microcrysts, sometimes you have these really horrible, especially like some of those andesites where you get this just chock full of microcrysts, and trying to find anywhere you can put a beam, even a 3 micron beam sometimes is just a nightmare. So all of these things, if you're trying to set up an analytical procedure, you have all of these different things that you have to worry about and end up kind of trying to compromise. All right, so here's an illustration of the alkali element migration effect. On the left side, this is the instantaneous count, right? So this is the X-ray intensity at a given time. And you can see it drops off fairly dramatically. The mafic tephra, more or less, in this case, these are pretty stable. It's more or less a horizontal line, so it doesn't really change much, if at all. There's an obsidian. This Lipari obsidian is one of a common reference material. Old Crow and Edziza tephras here actually behave somewhat similarly. Old Crow because it's really hydrated. Edziza because it has lots of sodium in it. and here they look more or less the same. But then when you look at least in terms of sodium, if you look at silicon or aluminum, then we can go to top right, and you could see the sample that has the highest sodium, the effect on silicon and aluminum of the sodium running away is a lot greater. Okay, and so if you think of, okay, well, what if I'm doing a 20-second analysis? What's that going to do? Well, now we need to think of the cumulative counts. So because at the beginning you were getting a higher count rate, and at the end you were getting a lower count rate, and it's sort of that all put together that ultimately controls what your analysis looks like. And so for the cumulative falls off a little bit more slowly, but you could see, let's say we go 20 seconds here for sodium. In these samples, we're down by 10% relative, and only a 20-second analysis time with a defocused beam or 10 micron beam, which is fairly common, and roughly 10 nanoamp current. That's pretty common conditions. And 20 seconds. A lot of people don't think that's very much time. We're down 10%. Okay, and it can of course get worse from there. And again, the effect on silicon and aluminum is less, and of course it depends on the sample. And so maybe you can run that a little bit longer unless you have a really sensitive glass like the Incisys sheet track. All right. So we very most definitely want to put the silicon and aluminum and sodium at the very, very beginning. What if you don't start analyzing aluminum until a minute after the beam was put on the sample? Now you're in that case, you're starting. Actually, well, really, we're starting. Our starting point is over here, and then you have to calculate your cumulative from there. So that's a major thing we have to worry about. And it turns out, even though this problem has been well known for a very long time, we haven't solved it entirely. We still are getting data, published data that's not necessarily got these quite right. All right. So this is some results here from this intercomparison project. So about 28 labs internationally, all active publishing Tephra labs, and you can see, for silicon, not so bad. There's mostly pretty good agreement there. A few labs kind of high, a few labs kind of low, but for the most part they overlap pretty well. If we go to sodium, now we're seeing a few. Okay, there's a few that are starting to fall apart. So this is the torture test sample with the 8 weight % or so sodium. Most of us aren't analyzing things like this on a regular basis. So if you can do this well, then probably you can do anything well. And so, but here's we have some bulk chemistry on. Well, I should say XRF and ICP, optical ICP, not trace ICP, on glass separates, and so that together with some of the probes where we know they're really taking the most conservative possible approach to this, they give us a target value of maybe about 8.2 on the oxide of sodium here, and we have some coming out an entire weight % low or even worse. And these are labs that analyze glass all the time. Okay, you're supposed to know what they're doing. Okay. So I think since this was done, a few of the labs that participated actually made some changes to procedures, and I think the state of things is actually better now. What about? We'll go down the next one. What about precision? On rhyolites, where that really matters most is on the minor and near trace elements, like magnesium. In some cases, it really is a trace element in rhyolites. Here we have, really you can see the difference between the EPMA and the microprobe and the few SEMs with EDS systems. EDS really has a hard time at low concentrations. I mean, detection limits are horrible. And some systems don't really even do anything very well under a whole weight percent. And so those standard deviations are the big ones, again, are EDS. But the probes are generally doing pretty well, and actually really quite comparable. So that's good. Okay, what about that precision again? So some of these tephras, we have very similar compositions. And if you have big standard deviations, how sure can you be whether things are different or not? Maybe the mean values seem to be separated, but they overlap. Is it the same or is it not? Well, what if your precision is better? Okay, so this is an example of that. So this is Glacier Peak, and I had the scatter plot of some of the majors on this earlier. And yeah, so here we have this apparent difference in mean compositions, but there's a huge overlap here. Okay. Would you say those are too different if that was all the data you had? Would you, if you argued that they would be different, how confident could you be? Well, what if maybe we shrink those standard deviations by half or a little bit more? Now maybe it's looking a little bit better. If we can shrink those standard deviations even a little bit more, then okay, maybe people will be a little more convinced. So our level of certainty in distinguishing things is in part related to our precision. And of course, advances in instrumentation and special techniques and things can help us with this. All right, so this intercomparison project, one of the things that came out of this was a bunch of recommendations for how to do things, and some of these were repeated from recommendations that have been around for a couple of decades before, sometimes refined, sometimes some new ones. So I have some of these interspersed in here. All right, so okay, we need enough accuracy and precision. Didn't I kind of already say that? Yeah. So yeah, the alkali element migration, we really have to keep a handle on that. And the only way you really know if you have it under control is to run reference samples where you know what the target value is and make sure your procedure is giving you what you should get. And if it's not, then fix it. All right. Here's another thing that sometimes we run across. How many of you have seen papers where there's a Tephra correlation and this is all you have? This is 100% of the evidence given. Yes. Okay. So-and-so said it's this Tephra. There's no data, there's no anything else but so-and-so said so. Okay. This stuff is still being published like this sometimes. Well, that's not so great. Okay. What about maybe we have actual data? We have means. Yay. Okay. Sometimes we even get standard deviations. Wow. I used to see, there's some analyses that are published where somebody will say, it'll give a mean value and then it says it was heterogeneous. What do you do with that? Okay, so we want at least some data. That is a good step. Standard deviations, okay, that's better. But we probably really do need a little more than that. So, okay, so here we have two samples. We've got there's our similarity coefficient, 0.95, the holy grail of similarity coefficients, right? If it's 0.95, it's a match. Really, isn't it? Yeah, look at the numbers. Wow, I mean 0.16, 0.14 on the titanium, 177, 176 on iron. Wow, this is great, right? Gee, even the sodiums even came out with, and potassium is amazing, came out with the same numbers. And like, gee, sometimes you run the same sample twice and you don't even get that. All right. Does this look like a match? How many people think this looks like a match? Yeah, okay. What about those standard deviations?
I know I'm being sad.
Can I ask a quick question? When you say standard deviations, you mean standard error?
This is the standard deviation of the the analysis points. This is not the same. This is not the same as the instrumental precision. Yeah.
Standard error is how well you know the mean. Well, standard deviation is the spread of the population.
Yeah, it's just these are just regular standard deviations. Just you go into Excel and you type equals STDEV parentheses and it points and calculates. Yeah. Just. Yeah. Yeah. I mean, these not too bad. I mean, so okay. But yeah, look at the standard deviations. Wow. Look at aluminum. You know what I really want? Maybe the mean in standard deviation isn't enough information here to really take a look at it. But so much, this is all we have. Okay, so it really looks kind of promising if you look carefully at the standard deviations. Okay, all right. Well, that was a first pass. These are the same two samples with more data. Okay, is it the same or not? You see why the means look so really similar, and why the standard deviations don't? Okay, so we really need all the individual data points. I mean, that really needs to be the way everything is reported these days. Okay. So if you have the whole population and you can plot it up and you can plot them against each other and look at them really carefully, you can evaluate things a lot more carefully, and your certainty as to whether things are the same or not. I think our certainty here is a lot greater than our certainty here. So, yes, publish the data, right? Okay. Yes, averages, it's better than nothing. Still not good enough these days. Standard deviations, adding that in, better. Still, I don't think good enough these days. You can't put the whole individual line-by-line data table in the actual publication because nobody will let you print something that's 100 pages long. So, but yeah, we have supplemental data and open databases and all kinds of other places we can put this stuff nowadays. So all the data, I want all of the individual analysis points, all of them. Okay, am I asking too much? Well, I know what it's like when you go through and you have all of this data and from hundreds of samples, and you spend an entire month doing nothing but putting together that giant supplemental data table. I know it's a lot of work. I've done it. I still want it anyway. Okay, less sleep. Oh well. All right, related to this, the similarity coefficient by itself, 0.95, okay, that's not good enough for me. Hopefully it's not good enough for you. Similarity coefficient is it's a very simple mathematical, it's just ratioing, very simple mathematically. And if you have a whole giant pile of data, it makes it very easy to sift through it and pull out things that look similar to your unknown, but it's a starting point. It's not the end where, okay, 0.95, we're done. It's the beginning to sift out the things for further scrutiny. All right. So here we go. Same or different? I sprung that other one on you. You're probably getting, I don't know if I want to answer this. This might be a trick question. Okay. These are all the exact same sample, different laboratories. These are individual data points. So I mean, you can look at the scatter of the results from an individual lab. It kind of gives you an idea of the precision, but that's about it. All right, how do we know if this is our problem? Okay. Well, that's where the secondary standards come in. That's really the only way you know, is take known samples. I mean, that's what that plot was. Same sample sent to a bunch of labs. Everybody analyzed the same thing. Now we know, are the results consistent between labs? Nick Pierce was just talking about this exact same problem. And one of the nice things is, to some extent, as long as I think we do have the sodium problem here on the bottom. Sometimes some things you can't really fix entirely, because every sample that you run might behave a little differently. But to some extent, if you have these reference materials and you have differences between labs, you can take those out. You could ratio everything to that reference standard, for example. That's one approach to handling that. But you can't do that if nobody publishes the data on the secondary standards. Oh, great. Now my giant supplemental data table that I just spent a month doing got a little bit longer. Okay. Oh well. But I still think it's essential. If we're really going to be confident in these correlations that we're getting them right, we really need this. 'Cause otherwise, can you really be sure? And then this has come up a number of times, and I think this is really where we're going, is getting that data more available. These open databases, and more funding agencies are starting to tell us, you have to have that data management plan and so on, and just keeping it in a spreadsheet on your laptop in your office is just not good enough anymore. And so getting that out more available, it would certainly make Jill's life a lot easier, and probably a lot of other people's lives a lot easier. And even put in there's a lot of these bits of data that maybe we're not really going to ever publish. I think some of that stuff should go in here. How many of us have our own sort of in-house database, and we have these random unknowns in there that we're never going to publish, and they might all match somebody else's random unknowns. Unless we put these things together, we'll never figure it out. I think that'll do.
Thanks, Steve. So I think we're still on time. We're delayed by 10 minutes because we started 10 minutes late. So we'll go ahead and keep moving along. Nelia Dunbar is our next presenter, and she's going to be talking to us about Antarctic tephra.
Okay.
Switch to the Windows.
Oh, right. Okay. Windows had crashed for some reason. Let's get a second to reboot here. I don't know why. I closed the laptop lid and came back later, and it was...
If you're having a hard time with it, I can just tell people what the axis is.
Yeah.
So if you prefer to do that, that's fine.
Let's see what it's doing here. I should have done that during lunch. It's coming. It'll take a couple of minutes. All right. This talk works better with Windows because a couple of the axes disappear on the Mac side. So maybe while Windows had crashed on here, so while I think it's restarting, yeah, maybe we could entertain a couple of questions or comments.
Questions about any of the previous talks?
I'm just watching a little black box, and Windows is booting up.
So you can answer questions?
Sure,
Okay,
I'll try.
Go for it.
Well, in that first little figure about the precision and accuracy for the individual labs, that precision, is that the external precision? So being just the standard deviation around the mean value, and how many analyses did each lab do?
Yeah, so it's just basic mean and standard deviation calculation in Excel, like everybody does easily. Nothing fancy. And we asked that generally there be around 15 or so data points. So there's a fair number. It should be reasonable. Yeah, they're not averages of 3 data points or anything like that.
It was 30 points, wasn't it? 30 points per
Maybe.
That's what I
Yeah. Okay. I think I encouraged 30, but I don't think we got 30 on
30 from us.
Okay.
And then one more really quick question, or actually a comment. When you showed us the error bars and you asked us to decide whether they're the same, I think another thing that really bothers me in the literature about correlation is that people assume that an error bar has equal likelihood of that value lying within those error bars at each end as it does in the middle. But you can imagine it's a normal distribution. So if you have some that are overlapping in just the latter portions of the error bars, then the likelihood of them being similar is much lower than you would think, because you're just looking at the tails of a normal distribution.
Yeah. Well, and we also have a lot of, there are plenty of tephra beds that are bimodal or have, you know, the population is heavily weighted towards, let's say, the higher silica end, and sort of tails off just a little bit to the other end, and we still calculate a standard deviation. Yeah, and it doesn't really tell you anything what the population distribution is, which is why you need all of the data points so you can plot it together and really see. And sometimes, yeah, that distribution where it's really weighted over here and there's a little bit over here, I mean, that can be reproducible and be significant. And yeah, and the standard deviations just don't capture it.
Right.
Okay.
From any of the talks?
Wait a second. This thing is not. I think this just went to 800 by 600. No? Make sure. Maybe it didn't.
Just a comment about the similarity coefficient. It has no statistical validity, so
yeah.
Because it's not a normally distributed function. It's very asymmetrical, so you can't use it to make any predictions or any probability predictions. It is useful to winnow out likely candidates. So it's useful in that respect. If you have a database of 7,000 or 10,000 samples, you can't eyeball them all at once. So you use this thing and you get maybe a dozen or 2 dozen candidates and you look through those. But I agree with what you said, that basically what you really want to do is present every single point. And the reason that wasn't done initially was that some of the early microprobes did things you couldn't do single shard analyses. You had to do them in batches of oxides in different sequences, and so you couldn't reoccupy the same shard.